Okay, maybe it's a good time to just formally start. So this is now the 15th lecture, and I'm going to cover today one of the more difficult and important topics in the moduli theory of stable curves, namely stable reduction. And I've outlined here sort of the schedule for the remainder of the course. We're sort of winding down. The UW quarter is ending actually next week. But I would like to give a total of 4, including this lecture. There's 4 lectures remaining, right? So today we'll cover stable reduction, which will have the implication that the moduli space of stable curves is a proper Deligne-Mumford stack. So yeah, we'll cover this today, but we'll probably go on and and recap and cover maybe more explicit stable reduction and some examples on Monday. And then we want to talk about gluing and forgetful morphisms because it's an important topic, and also we'll use it in one of our arguments for irreducibility. And I'd also like to cover the fact that this forgetful map is a universal family. And then moving forward, then we have just 2 remaining lectures. We'll have 1 lecture on irreducibility and then 1 lecture on projectivity. Great, but yeah, before I begin, are there any questions? Okay, I'm going to start as usual with a recap of where we are, and so I'd just to give us a summary of what we've shown is this theorem here, and I'd like to sort of connect the dots and to explain why we know all these things. So if we have this condition on the genus in N, this is just the condition that there exist stable curves, so the moduli space is non-empty, then MGN bar is a quasi-compact Deligne-Mumford stack, which is smooth and of relative dimension 3G minus 3 plus N. All right, so we more or less know this, but I want to review why we know this and sort of connect the dots of all the all the ingredients we have. So breaking this down into the different pieces is that we need to know that the stack is algebraic and locally a finite type over Z. And our approach was that we showed last time that the stack MGN of all proper curves is algebraic and locally a finite type over Z. And we showed this sort of directly using the Hilbert scheme by exhibiting smooth presentations from a Hilbert scheme. There's other ways to do this as well. It's actually, and you could also prove algebricity of the stack of all curves using Artin's criterions. This is how it's done in the Stacks project, and I think it's kind of a nice example illustrating the ideas of Artin's criterion to show it that way. But it certainly requires more work, namely using the deep result of Artin's criterion, which gives you sort of like local conditions to check for a moduli problem to know that it's algebraic. Right. So and then we also showed that stability was an open condition in families of curves, namely that MGN bar is an open substack of the stack of all curves. All right, and this allows us then to transfer the algebricity and the locally a finite tightness of the stack of all curves to the stack of stable curves. And as we mentioned last time, there are other ways you don't need to work with the stack of all curves. You could just show directly that this is an algebraic stack almost in the exact same way that we showed that MG without the bar was Deligne-Mumford and was algebraic. Great. So yeah, once it's algebraic, then to conclude that it's Deligne-Mumford, we need to know that for an n-pointed stable curve, The automorphism group, the abstract automorphism group. So this is abstract finite group. That we know, that was even one of the equivalent characterizations of what stable means for a nodal curve. But we need to know more than just that it's an abstract finite group. We need to know that the group scheme is a finite and reduced group scheme. And so we're going to use, for each of the next properties, 2, 3, and 4, we're going to use this proposition that's in the top right, which we took some work to show, but we did compute the dimensions of these X groups, and they control automorphisms, deformations, and obstructions. And namely that we know by deformation theory that if you take the tangent space at the identity of the automorphism group scheme, which I underline, that this is identified with X0 of omega c twisted by the points in the OC. Right, and the fact in the top right is that it's 0. And this implies that because there's no tangent space, the group scheme, we already know it's a finite type group scheme. So therefore it's actually a finite and reduced. Otherwise there would be a non-trivial tangent space. And then this was sort of the crucial ingredient in the equivalent characterization of Deligne-Mumford stacks. So by the equivalent characterization of Deligne-Mumford stacks, we conclude that NG bar is DM. So at least we've handled the Deligne-Mumfordness, and then going forward to conclude property 3 that NG bar is smooth, we use the formal lifting criterion. We've already used this once with MG, but let me just recall. So we use the formal lifting criterion, and what that says is, we have MGN bar over spec Z, and we want to consider sort of commutative diagrams where you have a thickening of local Artinian algebras, and you want to ask for the existence of a way to fill this in. So here, A surjecting onto A naught is a local homomorphism of local Artinian rings. And if we can even arrange that the kernel is a field equal to the residue field. So inside A naught, you have the residue field, the unique point, and therefore you get a k-valued point of the moduli space of stable curves. And let's just let that be, let's write that as C with marked points pi. Right, and now we use deformation theory. So deformation theory tells us that there exists an element, which I'm going to call ob, of the cohomology group X2 of omega c of OC, such that this element is 0 if and only if there exists this dotted arrow. But we know that that the entire X2 group is 0, so therefore the element is 0. So we win, and there always exists this dotted arrow, which means that the stack of stable curves is unobstructed and it's smooth. And then finally, again using deformation theory, just infinitesimal deformation theory, namely you consider, just consider extensions in this diagram where A is the dual numbers and A naught is the residue field. And then all possible extensions are identified with the tangent space of the stack M, G, and bar over Z cross K at this point C, Pi is identified with X1 omega C OC. Okay, and since this group we could calculate its dimension is 3G minus 3 plus N, we get that the relative tangent space has that dimension. And since it's smooth, that computes the dimension of the stack of stable curves. Great. So we have every adjective in this theorem except for the quasi-compactness. So let me also explain that. So what we're missing is the boundedness. And we'll use the fact that if we have a stable curve, then if I take the dualizing sheaf and twist by the endpoints and then take the third power, let's call that L, then this line bundle is very ample. Right, so I can use L to embed into some projective space. And if you want, you can compute that dimension using Riemann-Roch. It's just H0 of L. And we also have end marked points on C. Let's let P of T be the Hilbert polynomial. And then let's take the Hilbert scheme of subschemes of projective space, capital N. And the point here is we know this is projective. In particular, it's quasi-compact. And yeah, almost every boundedness argument in moduli theory eventually relies on like the boundedness for a Hilbert or a quote scheme. And so since that's, and I also have, since I'm considering marked points, I don't want to just consider these embeddings. I want to take the product with little n copies of projective space and then consider the incidence correspondence, let's call that H, of parameterizing the data of a closed subscheme in Pn together with n points in Pn, but let's require that the points actually live on the curve C. And so what we know is that this H, it's a quasi-projective variety. In particular, it's quasi-compact. And then there's a forgetful morphism from, like, if you just forget the embedding, you can map H to the stack of all curves just by sending, C embedded in Pn and these points Pi to just the C and the points Pi. Right, and inside here is our stack of interest, is MGN bar. And this morphism we've constructed, let's call it F. What we know is that, by this fact that this line, that the third power is always very ample, we know that the image of H contains MGN bar. Right, or in other words, if I take the fiber product of this diagram, H prime, that this map is surjective. And since H was quasi-compact, H prime is also quasi-compact. So depending on, so we conclude that this is quasi-compact. Okay. Any questions? Okay, I think we're in good shape. So now we have this theorem. The next goal is to show that it's proper. All right, so I'm going to start with giving sort of an overview of stable reduction. So by stable reduction, I mean, yeah, the goal is to show that MGN bar is proper over spec Z. Well, while that's the goal, I won't actually be able to show that. I think I'll give I'm going to be able to give an argument in characteristic 0. But let's think, what is it? So to show that MGN bar over spec Z is proper, the technique will be to use the value of criterion for properness, because I mean, this is one of the true value, like one of the true justifications for why we care about the value of criterion, is that we can use it in moduli problems, because of the functorial nature of these moduli problems, it reduces it to a very explicit question about the geometry of surfaces, you know. And so the value of criterion, there's a value of criterion for properness that I've stated here. So the condition is that, so I'll state it in the Noetherian setting. We have a finite morphism of Noetherian algebraic stacks. And then we want to know F is proper. And so it suffices to consider diagrams like this. So here spec R is, and throughout today's lecture, R is always a DVR. K is the fraction field. And so we think about spec R, you know, as a curve, which I'm going to use, I'll call delta, and then the generic point spec K is the open inclusion, so it's the puncture disk. And so you think about, you know, spec, yeah. Right. Okay. And then there's two conditions that you need. There's the existence, which is 1, and then the uniqueness. So for the existence, you want to find an extension, but you need, by the nature of, because of this is a stacky phenomenon here, is that you have to allow for extensions of the DVR. So what we need to show, to show that it's the existence, you need to show that there's some field extension K to K prime inducing an extension of DVRs and a dotted arrow filling in that diagram. And then the uniqueness is that you can just state in terms of this original diagram, if you have 2 ways to fill it in, then those 2 families of objects over spec R are isomorphic. Right, and if you just translate this value of criterion for properness, if you translate the existence part of the value criterion, you get stable reduction. So this is the theorem we're after, and it translates to the existence part of the value of criterion. So we start, then maybe I'll draw a picture here, is that we're starting with a family of curves, C star over delta star. Right, this is just the fraction field of a DVR. We're including it into the DVR delta. And then we also have maybe some sections. Let's call those, well, let me first draw the picture without sections. So in the on-pointed case, what we're asking is a way to fill in this family of curves over the DVR, but we need to allow for a base change here. So we take delta prime, and then you can consider delta prime, the restriction inside here. This is maybe spec K prime. And then you can restrict this over delta star to delta prime star. And this is what we want to fill in. We want to find a family of curves C prime over here, such that this is a stable family. And such that it restricts to the extension of the original family over K prime. And of course, if you have sections here, just to understand the notation, suppose I have sections Si star, I then want to find sections of this of this family Si prime, such that the two intersections to this one agree. All right, that's what we need to prove. And the uniqueness, or in other words, the separatedness, translates to that if you have two families, or suppose I have two families of curves, of stable curves over a DVR. So these are both stable. And suppose that when I restrict to the generic point, that I have an isomorphism. Let's call it alpha. Then you want to show that there exists an extension. Or that, yeah, you can extend the isomorphism of the generic fibers to an isomorphism of the total fibers. And similarly, if you have sections as well, like if you had sections here and here, then, and you had an isomorphism on the generic fibers preserving those sections, then you can extend in such a way that you also preserve those sections. Great. Okay, that's what the statement is. And maybe before giving an outline of the strategy, let me just give a few first examples of how this works in practice. So in this first example, we're going to be colliding marked points. So let's suppose we actually have a trivial family of curves. So this is C cross delta over your base delta. And if you want, you don't always have to think delta is the spectrum of a DVR. In these examples, you could just think of it to be an honest curve, like even A1. So I'm taking the trivial family, but I have three sections. I have, that are outlined here, sigma 1, sigma 2, and sigma 3. So this is a three-pointed curve. And note that away from 0, away from the central fiber, is that the sections are distinct. So away from the central fiber, you have an honest three-pointed stable curve. And we want to know what should be the limit when we fill it in. Right now, the central fiber is not stable because the 3 points are equal. And in this example, like explicitly, like if your base is maybe A1 with coordinates t, I have these local equations here. So t squared minus t squared and 4t. And so the natural thing to do, in order to separate sections, is to blow up. And so if I blow up once, then sigma 3 becomes, the strict transform of it becomes disjoint from the other two. But however, sigma 1 and sigma 2 still meet, right? Because they had a tangency condition here. So you need to blow up one more time. So we started by blowing up this point P. So you blow up P. And now we need to blow up this point here, Q. And now what you've arranged is that all of the sections are disjoint. But the central fiber is not stable. What I've drawn here, E1, is a rational, what I called last time, a rational tail, right? It's a P1, no, sorry, not rational tail. It's a rational bridge, right? Because this P1 here, this E1 meets the rest of the curve. Well, it meets the rest of the curve at one point, but you also have one section. So there's two special points. And then you just contract that rational bridge in the total family. So you just remove E1 and then you collapse. You take the image of this section and then it goes, and then it goes to, becomes, the sections remain disjoint and the central fiber is stable. Okay. So in our next example, we're going to consider the degeneration of a node to a cusp. So let's suppose we have a family like this, where I have a family of nodal curves. So and let's assume that the generic fiber is a stable nodal curve, but in the central fiber I have a cusp. So on the local equation of the surface, let's suppose it has this form: y squared equals x cubed plus tx squared, right? Where t is a local parameter of the base, and x and y are local coordinates on the surface. And note that when if you take the fiber when t is 0, you get y squared equals x cubed, and this is what we mean by a cusp. But when t is non-zero, the local, it looks like y squared equals, the singularity looks like y squared equals x squared, which is, our node. And the question is, what is the stable limit here, right? Like, we have a way to fill it in already where the central fiber is cuspidal, but we want to modify it in a way that's actually stable. And so what we do is let's take a section of this which picks out the node. So note that you can, maybe after base change, you can find a section that passes through these nodes, and then you take the partial normalization. Well, let me call it the pointed normalization. In this case, I just have one node, and because there's one node, there's then two sections. And so, and then if you consider this, like, this is what I've tried to draw on the right-hand side here, is that this is C star over maybe delta star, and that there you can, you realize that when you do this pointed normalization, you can fill in these sections in the total family. It's just that they intersect at this point here. So another way to view this actually is to think about this total family here as being like C cross C, and the base being C. And then you have two sections, one being the constant section, passing through where every point is P, and this other one being the diagonal, where you can think about maybe this is a point Q and you're sliding Q towards P. But now we're in the situation like we were before of the pointed case with sections colliding. We just blow up, and that introduces a P1, but this is stable now because there's three special points, and then you have to then you glue the sections together. So gluing these sections together then introduces again nodes in the generic fiber, and you get also a node in the central fiber. Right. So in this case, maybe I'll just spell out like is this clear? Maybe I'll just add. It's a good time to stop for questions. I think these are some of the simplest examples of stable reduction. But note that actually in both of these cases, like neither example is generically smooth. Or at least this example, is not generically smooth. And so if you wanted to consider a different family where you take y squared equals x cubed, say plus t, so this would be a smooth family degenerating to a cusp. The stable reduction is actually more difficult, and we'll get to it. Actually, the simplest examples are with sections colliding or nodes degenerating to a cusp. Okay, so let's see how you might handle a generically smooth family. So I'm going to outline now the basic strategy of how we're going to perform stable reduction. And I'm following the reference of Harris and Morrison. This is really where I learned it. I think their exposition is beautiful. Tons of examples which really provides some sort of geometric intuition for how to think about this. All right, so here's the strategy. We're given a stable curve over the spectrum of the fraction field of a DVR. The first step is just to find some extension to a flat family where with a possibly very singular central fiber. So what we want, yeah. So 0 always is going to denote the unique maximal ideal of R, the DVR, like the closed point of spec R. Right, so what we do is, well, you can just consider, you have C star over here, and you can just take the embedding of the relative dualizing sheaf. Oops. That embeds you into some large projective space over the fraction field. And we want to extend this to the DVR. But we have projective space over here, PNR. And yeah, the first thing you could do is you could just take the closure. You could take C, you could just define it to be the closure of this inside this projective space. Or in other words, the scheme theoretic image from C star into PN projective space over R. And you realize that, you know, this procedure of taking the closure doesn't introduce any new embedded points, right? So this map here is flat, right? And it's flat because all associated points live over the generic fiber, over the generic point. And you use a flatness criterion over smooth curves. Right, so this is great. This gives us some family, some C over delta, a flat family. But where the central fiber here, C0, is maybe very singular. Okay, so that's the first step. And maybe the second step, well, I guess you could have done this first, is that we're going to reduce to the case where the generic fiber is smooth. And this is very similar to the examples that I just outlined, where the idea in step 2 is, you know, if the central fiber has K nodes, just take the pointed normalization C star tilde, and since there's K nodes, there's going to be 2K pre-images, and then you perform stable reduction. And by properties of normalization, pointed normalization, we know that each connected component of this is also stable. So we can perform, and it lives over the generic. It lives over the fraction field of the DVR. So we can perform stable reduction to each component. And then you have to take, this requires some work, which we'll actually address more systematically next lecture. And we want to glue the sections back together. We take the nodal union of the sections. So yeah, and to get now and that gives a stable family. But note that for this induction argument to work, you need the pointed case. And this is sort of a general principle with MG. Even if you're just interested in properties of MG bar itself, often when you set up inductive arguments, you really need pointed case. You need to, it helps to also establish the pointed versions. And I think today, I'm often, for simplicity, I'm also, even though we need the pointed case field induction, for simplicity, I'm often going to assume n is 0. So that, yeah. Okay. So now we're in the setting where we have a smooth generic fiber, and we've already filled in the family of curves with possibly a very singular central fiber. And our step now is to take a resolution of singularities. And in fact, we take like an embedded resolution of singularities. So we're going to use, we use some tools in birational geometry of surfaces. And what it gives us is, so here's our original family, smooth generic fiber. So this is generically smooth. And then by taking a finite sequence of blowups of the central fiber, you get a regular model. So C tilde is regular. This map is projective and birational. And importantly, the pre-image of the central fiber has set theoretic normal crossings. What this means is if I take the reduced central fiber, it's nodal. So this gives us, I mean, this is a powerful, we're applying a powerful, like a result of embedded resolutions here. And it almost gives us exactly what we want, except that the central fiber may not be reduced. And just to convince you that this is really an issue that you have to address, that when you perform stable reduction, you always sort of end up with non-reduced fibers. Let me give you an example. In fact, we're going to take the example of a smooth curve degenerating to a cusp, where, let's say, the local equation looks like y squared equals x cubed plus t. And so this is a family of curves over a curve. Here's my central fiber. And let's think of this as just A1 with coordinates t. And here's my C. And let's blow up. Let's let this point be P. Let's blow up P. And see what we get. And so in the blow up, let's just look at like a local chart. So x tilde, y tilde. So this is just in one of the two charts. This maps to x tilde, y tilde, where this is our equation for x and this was our y. Right, and so now what's the central fiber of this blow up over A1? Well, it's the pre-image of the equation y squared equals x cubed. Y squared, let's write it as minus x cubed. And so we just have to rewrite that in, so let's go down here, equals. So if we just translate what x and y are, we get x tilde squared, y tilde squared minus an x tilde cubed, which we can factor as x tilde squared times y tilde squared minus x tilde. And notice that here, this x tilde is the local equation for the exceptional divisor, and we get two copies of the exceptional divisor. And what the picture looks like geometrically is that I haven't changed the generic fiber. I still have generically a family of smooth curves. And now the central fiber looks like an exceptional P1 meeting the rest of the curve in a sort of, tangentially, as pictured, like, right, because y squared minus x is, it's like the parabola, meeting the vertical line. And so you see here that the central fiber set there's two copies of the exceptional divisor, both non-reduced. Okay, so that was step 3. I'm not gonna quickly summarize the next 2 steps. This is where all the action is. So on the left-hand side, I just sort of summarized where we were. This is just the first 3 steps as I sort of explained. And now step 4 is you want to make the central fiber reduced, and so you perform a ramified base extension such that the central fiber of the normalization of this is reduced in nodal. And so yeah. And yeah. And then the final step, once you do that, once you make the central fiber reduced to nodal, so now you're now you have a family of nodal curves, and you can take sort of the relative stable model or the relative minimal, and you just contract the rational tails and bridges. So these are the 2 steps. I'll give more details on 4 and 5. All right, yeah. So I owe you these details, but I'd first like to pause and take questions. And drink some more coffee.
Why do you perform step 2 after step 1?
Yeah, I think you could, maybe it would be more natural to perform it first. Yeah. Yeah, actually, I think I like performing it the other way around. Yeah. Yeah, the reduction to the generic fiber requires knowing about partial. The reduction to the case where the generic fiber is smooth requires taking the partial normalization and then performing stable reduction in the pointed case and then gluing back sections. And there are some details there, and I think actually after Wednesday's lecture, next Monday's lecture, I'm going to talk about how you glue sections and how that produces natural maps between these moduli spaces. So I think I'm not going to give more details today on that step. But what I really need to explain is how we can do this. But first, I'd like to give a recap of sort of the birational geometry of surfaces that goes into this argument. Okay, so here I have 4 facts up there from the birational geometry of surfaces. But let me first explain this really kind of this principle in moduli theory of varieties. Is that if you're interested in understanding the moduli space of n-dimensional varieties, and specifically say you want to find a compactification of the moduli space, and you want to determine sort of what singularities of canonically polarized dimension and variety should I allow to get a compact moduli problem, it requires sort of a systematic understanding of birational geometry in one higher dimension. Because via the value criterion, you're sort of forced to study families of objects over a curve, and therefore you've increased the dimension by 1. And sort of if you can understand the minimal model program in dimension n+1, that gives you some insight to stable reduction. Namely, you should apply the relative minimal model program in dimension n+1 over your curve, and that should produce the stable model. So for us, we're interested just in the case of curves, and so we need to know stuff about the minimal model program for surfaces. Right, and so here, by a surface, in the statements below, I just mean, I mean an integral scheme of finite type over a field of dimension 2. But we apply this to curves over a DVR, and it also works in that setting. And the references for this, all these facts are in Hartshorne, chapter 5. And another nice place to read about this is Kollar's notes on lectures of resolutions of singularities. So the statements we need, the first one is embedded resolutions, which which I've already explained why we need it. Maybe I won't even repeat the statement here. You can read it. And some of the other nice facts to keep in mind, what we will use is that you could find minimal resolutions for surfaces, and that they're unique, and that given a surface, you can find a resolution of singularities, x tilde to x, such that every other resolution factors through it. And then something hopefully is familiar is this contraction theorem due to Castelnuova, which says that if you have a smooth rational curve, like it's a P1 inside your surface with self-intersection -1, then you can blow it down to a smooth surface. You can also blow down other exceptional curves with have maybe where e squared is -2, say, but you can still blow them down, but you lose the smoothness. And if you apply, this is if you can show this, you can show that the process of contracting -1 curves terminates. And so what you arrive at is, when you contract all the -1 curves, is what's called the relative minimal model. So given a smooth surface, contracting all of the -1 curves gives you the relative minimal model, which in particular has no other smooth rational -1 curves. So yeah, these are the results that we're going to be applying. Okay, so back to the proof, and now I'm gonna, okay. So here's a proof of stable reduction, and this is, I'd like to highlight this. We're giving a proof in characteristic 0. Okay, so our setup again is we have a family of curves over spec K, and the first 3 steps, I think we're comfortable with. They involved reducing to the smooth case, finding some possibly horribly singular limit, and then applying embedded resolutions. And what that gives us is, this gives C over delta with the reduced central fiber nodal. And the total family regular. Right, so in this picture, we have C, we have a flat family, and a total family here is regular. Okay, so now in step 4, we take a ramified base extension. So this is just a base change of DVRs, where defined by t goes to t to the m. Right, these are t is the uniformizer in the DVR. And what do we take for m to be? So we take m just to be some integer dividing all the multiplicities of the central fiber. Because if you want, you could take it to be the lowest common multiple of the multiplicities of the components. Okay, and recall that we have an État local description of this map near, so really any point in the central fiber. And it sort of depends on 2 cases, whether it's smooth, if P in the central fiber, and the reduced central fiber is smooth, then this map looks like x to the y goes to x to the a. So in this case, the central fiber is smooth. Oh, that's looks like smooth, but it's thickened. So your point is here, and you have multiplicity A. Like it looks like it looks like x to the A equals 0. That's the local equation of the fiber. If the central fiber is nodal, then this map looks like x to the A, y to the B, where now you have two components that are thickened, and your point is the intersection. And so we're gonna handle both of these cases sort of separately. We're really trying to we're taking the base change, t goes to t to the m, and what we'd really like to understand is not just c prime, but its normalization. So let's just this is sort of a local calculation. So for one, P in the surface has a local equation x to the A minus t, right? T is the local coordinate of the base. So when t is 0, the fiber is x to the A. And there exists a unique preimage P prime and C prime, which was C cross delta over delta prime. And this has a local equation given by x to the A. We substitute in t to the m, right? Because that was our base change. And the point is that we took m large enough such that A divides it. So this factors, and now we're going to be using characteristic 0. Let me highlight this. So we can then factor this. Where rho is a primitive eighth root of unity. And what you note is that in characteristic 0, this is reduced. And you also see what happens in characteristic P, right? If your multiplicity of some component is P, and then you take this ramified base change, T goes to T to the P, you're not going to improve the situation. Because it's not tamely ramified.
Do you not have to
right, and then
do you not have to take the normalization?
Because
if it starts non-reduced, won't the special fiber still be non-reduced if you just do this base change for Z prime?
Yeah, I think I've introduced. I think they could intersect, right? And I think I want to take the normalization. So now that these local equations no longer intersect.
Right. So C prime is the normalization of the base change, or just the base?
No. Now I take. So I think what I want now I take C tilde prime, the normalization. And this has a preimage P tilde prime mapping to P prime, and this has local equation, like just one of these components. And so what we see is that, okay, I ran out of space, is that, let me write it here. What this implies is that this new point is still smooth in the central fiber. So actually, this point is a smooth point in the central fiber, and it's a smooth point in the total family. Okay, and now, right, let's also handle the other case. So let's consider the case where this is a node in the reduced central fiber. So this was the local equation here was xy goes to x to the a, y to the b, and maybe I'll leave this is a slightly more difficult local calculation, but under the normalization, there's each pre-image say p tilde prime of p has a local equation that looks like t to the k equals xy. And what this tells you is two things. Well, if it tells you that this point in the new central fiber is nodal, reduced and nodal. And it also tells you that the point that in the total family may be singular, that this is an ak minus 1 singularity. Let me finish the argument and then take questions. Just about to wrap it up. So in the final step now, so the upshot here is we have c tilde prime to delta. Let's replace. Let's just call c, replace c with c tilde prime. We get a nodal family where now this may have singularities. But that doesn't really bother us because in step 5, the first thing we're going to do is take a minimal resolution. So now we'll replace C with a minimal resolution. So this gives C over delta. And now I have, now it's really a pre-stable family of nodal curves. And this is regular. And so at this step, we can take, if you want, you can take the stable model. By contracting rational tails and bridges, like we showed in complete generality, I think last time. So this gives you C going to the stable model over delta. And now this is a stable family. Actually, but you know, since we've taken C to be regular here, you can explicitly see this process here. You don't need the full power of you know, the contraction of rational tails and bridges. We're just working with, you know, a family of curves over a curve. So we can use surface theory. And so explicitly what we're doing here is you could view this in 2 steps, right? The first thing you're doing is you contract rational tails. So these might look like, you might have a family of curves like this, where the central fiber is just a P1 like this. And what we've seen is that E squared here is -1. And so you can contract E by Casalanova. And then what that gives you, if you contract all of the -1 curves, and you show that that process terminates, that gives you the relative minimal model. And now now the total family here is still regular. And this is now, there's no rational tails anymore. So this is a semi-stable family. And in fact, you could stop at this step. This gives you, you could call this the semi-stable reduction, where you've filled in the central fiber in a way that the central fiber, you filled it in your family so that the central fiber is semi-stable and that the total family is regular, which is a desirable property. But if you want a stable family, now you just contract the rational bridges. These are -2 curves. They can be contracted, but they introduce singularities, but it gives you this stable model. And I think, yeah, okay. That wraps up the characteristic zero proof. Any questions? In fact, I think I'm doing well with time today. I think we'll have enough time for a discussion. So let me, I have one more slide, and then then we could just have a more casual discussion. So I'd just like to give you a summary of what we proved here. Right. So in characteristic zero, we've shown two things. We've shown the semi-stable reduction and the stable reduction. And some history here. In the original seminal paper by Deline and Mumford, they didn't consider the pointed case, but they proved this. They showed stable reduction. Like in general, maybe I should highlight that our proof was characteristic zero in positive or mixed characteristic. But relying on stable reduction for abelian varieties. In other words, they could, by associating to a curve as Jacobian, that they showed that stable reduction for curves is the same as stable reduction for varieties, and this was already known at that time. And even historically, stable reduction, for the moduli space for abelian varieties was proved to exist before MG bar algebraically. And one of Mumford's first arguments for the existence of MG relied on the moduli for abelian varieties. This is sort of a common technique to rely on it. But certainly their proof is not elementary. Neither is the And then shortly after, Artin and Winters, this is around 71, they gave a proof again that works in positive or mixed characteristic, like vaguely along the same lines as what we presented. Namely, here's just a very vague idea, and I would encourage you to look at their paper, or you can read about this in the Stacks project. There's a very nice exposition there with a much more detailed reference list including a variety of other articles covering stable reduction. So the vague idea is that, like, here steps 1 to 3, what they give you is it gives you so we have C star. So those, yeah, so you get a family, a flat family, and you can even arrange that the reduced central fiber is nodal. Namely, you can apply embedded resolutions and positive characteristic as well. But it's really at step 4 where we used positive characteristic, where we took an explicit, a ramified base change in order to make the central fiber reduced. That doesn't work. And their idea seems really magical to me. You take a field extension such that you can arrange two things. So, well, such that, first of all, let's just take the base change to spec K prime. So let's call that C prime star. Or, yeah, maybe that's too many primes. Let's call that C star over K prime. So first you can arrange that this has rational points. That there is a K prime point. And maybe more importantly, that you can arrange that the Picard group that the L torsion for a large enough prime is just 2G copies of Z mod LZ for L sufficiently big. In particular, you want it to be distinct from the characteristic of the residue field. And then you take a DVR, R prime, and you somehow magically show that this process works, that the central fiber of C R prime is reduced to nodal. I mean, I think this is a vast oversimplification, and I'm not an expert enough, and I haven't worked through the details, but sort of my vague understanding of this. But yeah, I'd like to just conclude on that note, and we have time for a discussion today.